Thank you for tuning in. This is Kijeshwan. We're working to be the center of physics. Welcome. Today we shall discuss on Hooke's law, a chapter that seems to be difficult at the start, but also very challenging amidst it. So, welcome. So, here is the title. In this case, we shall be looking at all things to do with the application of forces and what a force can cause to a material that is elastic. And most probably, we shall be talking uh, on springs and elastic materials. Before we can go straight to the introduction parts, uh, characteristics of materials. We have the strength, and you can see that it is the ability of a material to resist a breakage when under stretching or compressing or shearing force. Then you are even told that a strong material is one which can withstand a large force without breaking. We have property or characteristic number two, and this is stiffness. And stiffness is the resistance a material offers. It's a resistance a material offers uh, to forces which tend to change its shape or size or both. Uh, Allow me take a minute to share the links. This is always a free platform. If you are a student or a teacher, maybe you can gain something. Remember, learning is always in a progressive manner. I'm just taking some few minutes uh, to share the links so that others may also join us. I'm not going to take long. So we are in the third one. That one is ductility. And in ductility, it is the quality of a material which leads to permanent change of size and shape. Materials which elongate considerably under stretching forces and undergo plastic deformation until they break are known as ductile materials. We have several examples here. We have lead, we have copper, we have rods, we have iron and plasticines. Remember, ductility is also mentioned in chemistry. Ductile materials can be rolled into sheets, can be drawn into wires, or worked into other useful shapes without breaking. Uh, from here, we'll be looking, sorry, can also finish with the characteristics. They are several. We have several which are painting. We have brittleness. This is the quality of a material which leads to breakage just after the elastic limit is reached. Brittle materials are fragile and do not undergo any noticeable extensions on stretching, but snap suddenly without warning. We have the chalks that are used for the blackboards. We have bricks, we have cast iron boards, glass, and dry biscuits. They are some of the examples of materials that break without notice. We have elasticity. Uh, this is the ability of a material to recover its original shape and size after the force causing the deformation is removed. A material which does not recover but is deformed permanently, that is plasticine, is said to be elastic. We have now the last property of stretching of materials. We expect if a material is stretched, we expect its length to either increase or decrease depending on how the applied force of stretching is acting on. Briefly, I'll touch on stretching of a spiral spring. In this case, we all know that the moment you apply force on a spring, for example, taking an example of that a spring is of such a length like that. Can call this one L in centimeters. Then now it is free. Then you apply some weight or some mass in it. And now we expect the total length now to be X, because now here you are applying some force F. So on application of force, the spring extends. In short, it increases in length. Therefore, you can say that the extension E will be given by the total length after applying force minus L. And because in our diagram we are talking in centimeters, this means that if we keep on adding the force, then we shall also keep on having elongation of the extension. So if you have addition of the force or the weights or the mass increases, then we expect E to keep also extending. Then it is from here where we shall derive that the moment you keep applying this force, the applied force F, this one is always in newtons, then it is going to produce extension. The extension can either be in centimeters or in meters, but we shall talk about it in a special graph. And therefore, we expect that the moment you try to increase the acting force, you also do increase the extension. And it is from here where we derive now the Hooke's law. So the moment you try to increase the force, also the extension is increasing. Therefore, you can say Hooke's law, therefore, is stated as for an elastic for a helical spring or an elastic material, the extension is directly proportional to the force causing, can say, to the stretching force provided that elastic limit is not exceeded. provided that the elastic limit is not exceeded. So now, before we move now to the explanation of that, can still visit uh, this equation or the state. Hooke's law. It is here now. You can view it directly from the screen, where it says that for a helical spring or material, the extension is directly proportional. I think, okay, is directly proportional to the stretching force, provided that elastic limit is not exceeded. Now we can get back to this, what we are talking of. So in this case, you will say that in summary, we are trying to say that force is directly proportional to extension. Therefore, we include a constant here. We can say F is equals to a constant times extension. And in this, our K will stand for either, it's just a constant, but because mostly we are dealing with springs, in this case, you can say it is the spring constant. Therefore, from this, we can call this one the special equation 1. Then we can say that spring constant is called is force over extension, our equation 2. And then extension is given by force over K. This becomes our equation 3. So majorly in this chapter, we'll be dealing with these three equations. If you look at the spring constants, we haven't mentioned clearly about it. And being, we have said that spring constant is given by force over extension. Remember, this force is supposed to be in newtons. And then the extension is supposed to be in SI units of meters, because extension is like a distance. It is like a distance. Therefore, now from this one, because you have said that provided that the elastic limit is not exceeded, then the force which is directly proportional to extension, then that is Hooke's law. But now, what about when it happens that you're having a graph like this one? Force of, that is graph of F against extension E. What will be happening here? This is now the stretching force, and this is our extension. This is our extension. Therefore, from O to E, from here all the way to E, or E, OE, we can see that our F is directly proportional to extension, meaning that The material that is being tested there will be obeying Hooke's law. We can have a look at the explanation. But the moment the force goes beyond point E, then we start saying that EB, this is permanent deformation. In short, if you stretch a spring, then it will not get back to its normal position. It will not get back to its old. Now we can continue. So at point E, we can say that is where the elastic limit is. Therefore, any excess force that will be applied, and once it is withdrawn, then either the elastic material or the spring will let get back to its normal position. Then we may now proceed. Therefore, to explain this graph, because it is highly tested, then you should be very careful with it. And the moment you are doing explanation with graphs, then you should explain in what the graph represents. Now, let's look at now the special parts of this graph. Of force against extension. That is now the graph. Then it come a time what will be the representation of this graph. Number one, you can see it is force against extension. Meaning that if you are looking for the slope, Then it will be change in force over change in extension. And then this one will translate to us that this one is directly giving us the spring constant. It is directly giving us the spring constant. We may proceed to the next parts. Might becoming invisible, but the most important thing is that you see the working area. Then now we may proceed. Uh, we know that a spring has potential, elastic uh, energy, or we can say work done. Therefore, work done by a spring is said to be to the area under the graph. How? The graph is like this. Then it is in a triangular manner. Therefore, we just say that work done is same as half times force times extension. Remember, hold this one. You should substitute use SI units. This case. Therefore, work done by a spring will be half Fe. But now, if you get back to the Hooke's law, where we say that from, let me check which equation, from equation 1, where we say that force is given by Ke, force is given by Ke, then but F is given by Ke. So if you substitute this F with Ke, then we'll arrive at, you can say this is the first one. You can also say, or work done is given by half times Ke times E. This will lead us to work done is given by half Ke squared. And remember here, we're supposed to give units are always in joules. I do not understand why I have become black, but no problem. Uh, we can continue. Uh, Factors affecting the spring constants. But before I move to that, allow me touch on a deeper explanation on these two graphs. Graph number one, a graph of force against extension. A, E in centimeters, and B when we have extension in meters. This is force F against extension. E in centimeters. So for this case, if you have to say that you want the gradient, then the slope, which is giving us the constant, would be change in F over change in E. This is Newton, and this is centimeters. Therefore, the overall units here will be in Newton per centimeter. What about when we are having the extension here in meters? Then the constant will be change in F over change in E. This one will be Newton. The constant will. Therefore, we can say that SI units for spring constant is Newton per meter. Then sometimes you can be given a question that is in Newton per centimeters. Therefore, to convert Newton per centimeter to Newton per meter, then you divide by 100 or multiply by 0.01. For example, you're told that 2 Newton per centimeter. You want to convert it into Newton per meter, and this one will be 2 divided by so we can ignore these parts. And we can say then U divide by 0.01. So this is 2 divided by 0.01, and you're gonna get 200 newtons per meter. Yeah, it is okay even when you say or multiply. Multiply by 100. Then we have graph number 2. A graph of extension against force. It still appear the same, but now in this case, so change in E against change in F is our slope. So what will be our slope? If you look at this one, it is like K is equals to force over extension. So if you relate this one to be like this, now you will start with E over F. It will be represented 1 over K. Therefore, our slope here will be representing 1 over K. Therefore, for us to get K, then you must get the inverse of the slope. Think now in our next lesson, we shall look at some of the examples. But before I conclude, we can briefly look at factors affecting spring constant. They are here, number. They are 4. We have the type of the material that is used in making the wire. We have the length of the wire. Remember, length of the wire, if it is long, then probably we expect it to have weak spring constant. We have the number of turns per unit length. If you have so many number of turns, then we expect it to be of weak spring constant. The diameter or the thickness of the spring. This one, we are talking of this diameter now. This, not of the wire, but the diameter. So if it is having a very large diameter, then we expect it to be of weak spring constant. But if it is having very small diameter, this one is strong, this one is weak. Then now you have the last one, you have the weakness, the thickness of the wire. It is obvious that the thickness of the wire will be of importance. We have already visited the work done in stretching a spring. We have already done it in my KDH1 online school. Therefore, tomorrow being another day, we shall continue with the now some of the examples in calculation of spring constants. Then have a blessed evening and thank you so much. Don't forget to share. Ensure you build this one to reach as many people as possible. My only saying will always be there is no way a candle will lose something by lighting another candle. Remember, if I grow, you also grow in one way or the other. Thank you so much. See you in the next lesson about the spring constants, combined spring constants, the arrangements of these spring constants, the series, the parallel connection, and then we have the series parallel connection. And then we shall finish this chapter.